Hello. Can anyone, can someone confirm that my audio uh, is working on it? Yeah. Hello. Hey, Shantru, can you hear me now? All right. Let's start. Okay. Welcome to Geometry of Data. What we'll do today is that we'll continue our discussion on diffusion models. Today we'll do conditional diffusion models and see what is the difference between basic neural networks that we had, diffusion models that we had seen, and how can we make it conditional, and what is the benefit of making having a conditional diffusion model. We'll see that demonstrate that using one example, which will sort of show us one practical scenario where conditional diffusion models can sort of help you generate data in a way that you want. After that, we will then discuss some graph neural networks. In graphs, what we'll see is that how a normal graph neural network works, and also how you can design a graph convolution neural network and what kinds of data you can process with that. So yeah, just a basic introduction on conditional diffusion models and graph neural networks is what we'll cover today. If there are any questions online, you can feel free just unmute yourself and just say something, or also you can just put it in the chats. I see there's more people online today, so yeah. All right. So we had seen that a diffusion model. All right. Okay. Also, we are referring to the slides. If I share my slide here, the problem will be that you won't be able to see the board anymore. So what I would suggest for people online is that you pull up the slides on your own end, and then sort of like just follow the content that's like we're referring to on the slide. Maybe if I can make the camera sort of display the slides separately, that would be. Wait. Perspective. Yeah, I don't think we can sort of fix the camera. All right. So yeah, so just follow the slides on your own devices, and yeah, it'll be fine. I'll write everything on the board anyway, so you can sort of refer to that. All right. So conditional diffusion models. Let's quickly sort of review what normal diffusion models are first, very briefly, and then we can see what conditional diffusion models, how they are different. So overall, when we're training like a diffusion model, what we are trying to do is that we're trying to train a denoising neural network, which takes in like a noised version of an image and then give us like a clean version of the same image. So for example, if you have an image like this, and you add like a certain amount of Gaussian noise. And this Gaussian noise can be sort of can refer to like any amount of noise depending on how many time steps of noise you want to add, because neural like diffusion models are designed in a way where you are incrementally iteratively adding noise to these images by a small amount at a time. So it sort of accumulates into a lot of noise, and eventually after t time steps the image is completely converted into noise. So given an image with some Gaussian noise, if you pass it to, let's say, a denoising neural network model, what this should give you is just give you the image back, right? So it should already remove all the Gaussian noise and you get the image back. And we had seen that this kind of a setup works better if you, instead of predicting the clean image, what you do is that you predict the Gaussian noise itself. So you sort of, instead of predicting what the image is, you predict the amount of Gaussian noise that was added to the model. And you know what the Gaussian noise was that you added, because this is something that you sample yourself. You know what this should be. Like this should be exactly equal to this Gaussian noise that we have added. So you can compare like these two with like an L2 loss, and then a gradient on this L2 loss will sort of help you optimize the parameter theta, right, of this neural network model. This neural network models has parameters theta, and then you sort of optimize on them, and you're able to sort of train a model which can remove all the noise from an image, right? But let's say we want to make this conditional, and by conditional I mean that the model should be able to sort of take into account a conditioning signal, and this conditioning signal could be of any type. Like it should be another form of data that you give to the model, that model should take into account before it's generating the image. Okay, so the most natural way to condition these models is to condition it using text. Like we discussed in last class, is that language is the fundamental way in which we sort of share information with each other. We also sort of understand all of these concepts and all of the things that we see in images as textual words and as a like an abstract representation of the information conveyed by the image can be represented using informative enough textual captions. So for example, on this image, if you look at the content of the image, you can summarize the content of the image as a descriptive caption, and then this caption sort of already is very informative to the user, and then you can sort of change this caption and try to change the content of the image. So because language itself is such a fundamental way to control information and to sort of transmit information, what we would want is that a conditional diffusion model, if it's generating images, if it can be conditioned on language itself, what you can then do is that you can control it with the most natural way to compress information. Like you can just say things in text, and then the model will be able to sort of generate images that agree with that text, right? So you condition the model on some textual caption, right? So for this type of training, what you would then need is that you have images and also have the corresponding captions, right? And once you have these captions, what you want to do is that you condition your neural network model also on the captions, right? So in addition to this neural network model getting a noised image from this noising process, it also takes the captions that sort of go with that image, right? So if there is an image of a dog, the caption could just say that this is a picture of a dog. And then the neural network model, in addition to having a noised version of that image, also takes in the caption and then denoises the image by taking the caption into account, right? So the only thing that you're changing is that the posterior function that we were sort of approximating as a neural network here, where the neural network has like two different branches. The first branch is predicting the mean of the neural network or the distribution from which we are sampling the image, and the other neural network is predicting the standard deviation of the distribution from which we are sampling these images. So these two neural networks, which sort of predict the like properties of the distribution, also now take into account the C conditioning signal. So this C is the same as Y in the text. So just make that assumption that all the Y's here are just C. So in this neural network model, you'll see that this, in addition to taking the XT, which is the noise image, the time step, which is like the amount of noise, like just an indication of the amount of noise that was added to the image, will also take in the conditioning signal. So you can see here that this model that we're talking about, which is exactly what a mu theta or a sigma theta model would look like. You can imagine that this neural network is just two branches. The first branch is predicting the mu, and the second branch is predicting the standard deviation. And both of these are predicted by taking three things into account, which is the image with the noise in it, which is like XT, the amount of noise that was added, which is T, the time step, and also the conditioning signal C, which is the caption. So by taking all three of these into account, then the model is able to predict X, T minus 1. Does that make sense? Right. So a fundamental question that you should have now is that how are these models sort of taking any kind of information into it and still sort of are able to process these different modalities together. Like for example, that this is an image like xt and t. T is just a unique like one vector which is just one value. Xt is an image, but c is like a vector which is represented which is representing the caption, right? You don't directly feed in the text into the model, you convert the text into like a representation, and then you feed in that representation to this model. So how is this model able to take in all these kinds of inputs and still function normally? So these are some practical considerations on the slide. You can see that there are three ways if you are trying to condition your diffusion model on different types of information. There are different practical considerations or practical tricks that sort of work in recent literature. If you want to condition it on a scalar, which is just one value, like for example, if you're trying to, let's say, generate different types of flowers, and there are only 5 flowers in your data set. So instead of representing the names of the flowers as like text, you can also represent the 5 flowers as 5 different scalar values. Because there's only 5 things in your data, you can just condition, instead of conditioning it on the caption, you can just condition it on one value, where each value would represent a different type of a flower, and the model will then sort of learn different categories just using that scalar as like conditioning thing. So if you want to consider sort of conditioning your model on a scalar, you can encode the scalar as a vector embedding, and then you can directly either just spatially add this vector embedding into the representations of your model. And this model is generally a unit model. And why is it a unit model? Is because it's always taking the input, which is the same size as we expect the output to be, right? Because it's taking the XT image, which is the same size as the original image with just some noise in it. And you're predicting the Gaussian noise, which is also like the same size as the image, but it's just noise. So it's just like a, two, let's say 28 cross 28 dimensional noise. And these images are also, let's say 3 cross 28 cross 28. And 28 cross 28 is just like a very small example of a small image, but this could be like whatever this size is, will be the same size as you expect as the output. And models that sort of are able to do that, which take in the same size as the input and output the same size as the output, are usually called unit models. And these are the ones that work the best in situations like this. So you use a unit network, and in the intermediate layers of the unit network, you just spatially add or adaptively add like the vector embedding, which represents the scalar that you want to sort of condition this diffusion model on. And that would automatically sort of input, like sort of feed in that information that you want to condition it on. And because of the loss being designed as such, the model will automatically learn how it needs to use that information. All right. Similarly, if you want to condition it on an image, like for example, if you were training like a model that takes in, let's say, a video of the frame and is predicting the next video of that, a frame of a video, like you take like one frame from a video and you train a model to predict the next frame from that video. And this can be used to sort of increase the FPS of a given video by sort of adding another frame between the two frames that are already recorded. So things like that, where you want to condition it on other images to generate more images, is where you need some image conditioning tricks. And if you want to condition on image, the easiest way is that you just sort of resize the image as the size of the feature dimension in the unit architecture, and just concatenate it wherever possible. So at the intermediate feature representation, just concatenate the representation of the image as the same size as the feature dimensions, and then that would also sort of input that information into the diffusion model. Similarly, for text conditioning is the same as scalar conditioning. You just convert the text using, let's say, a clip model or any model like that, which can take in like a textual caption and convert it into a vector. So once you take this caption, you pass it to the clip model, you convert this to a vector, which is a representation of that text. And then this vector can again be added spatially or using like a group normalization layer into the intermediate representations of the unit architecture that you're using for denoising this model, right? So practically, depending on what kind of information you want to condition this model on, there are different architectures that work. And recent literature and upcoming literature also trying to come up with different types of different types of practical tricks that sort of work for these models. All right. So after all of this neural network training, like for example, there is a case where you only, let's say, train a diffusion model unconditionally. Like the model is completely trained unconditionally, where the model does not really take into account any extra information to generate an image. So if you train a generative model like that, like if you train a diffusion model only on just images, what will happen is that when you try to sort of generate more data from that model, the model will randomly start generating images which look similar to the images that are in the dataset, right? But you don't have any sort of control on what image it will generate. Like it will just generate a random, like for example, if you train it on a dataset which has like a lot of animals, right? Like it's just different images of different animals. If you train a model like that on just this data set and then try to like generate more images from that model, what will happen is that the model will start generating random animals. Like you'll get a dog in one iteration, then you'd randomly get like a cow, and then if you generate again, you get a horse. So things like that will start happening, but you have no control over which animal you want to sort of generate, right? But there are tricks to sort of still be able to get some type of conditional signal into the model, even when the model is trained completely conditionally, completely unconditionally, right? And you do that using a classifier model. So the idea is that even if we don't have, let's say, a model that can understand different conditions, if we have a classifier model that can take in an image of an animal and predict what animal that is, you can already use the gradients from this classifier to sort of inform the generation process of the diffusion model to generate an image which would agree with this classifier. Right? So here on the slides, this is what the model is, which is just predicting the mean. You can see that the standard deviation is now not predicted by the model. So you just have like this, the model predicting what your distribution is from which you want to sample. But you also want to take into account this classifier gradient. And these two models, like the classifier itself, is completely independently trained. So you can have like a separate classifier which is trained on a different data set, or like a completely different model setup, as long as it's able to identify images of animals and you are trying to generate images of animals, it will still work, right? As long as this classifier is able to give you gradients, which is just trying to predict like a certain class from a given image, right? So yeah, let me just write out the equation for this. Okay, so we have our model P of xt, sorry, P of x naught, which is just generating the data. And what we also have is that we have a score model, which is what your classifier is. So I'll just say the classifier model, which is P of y given xt. Right? And what does this mean? It takes in an image at the time step t, which is like sort of a noised image. And it tries to predict the class of that image, right? So in our example, this will take like, let's say, a noisy dog and predict the probability of this image being a dog given xt, right? So these are the two models that you train. And now what you want to do is that you want to sample from an unconditional model, which is not really, does not really take the condition into account, but still sort of go towards that. So what you do is that you compute a gradient in the image space itself, because if you recall, all of these sort of diffusion models are directly working in the pixel space, right? Because the image itself and the feature representation in the intermediate time steps and the noised images themselves are all the same size. So the latent code in this model, different from a variational autoencoder or an autoencoder, is the same size as the image itself. So the latent representation is directly embedded in the manifold in which the images reside also, right? So because of that being the case, what you can do is that you compute the gradient with respect to the image space itself, like gradient with respect to xt of this model, of the log probability of this model, right? So you have p phi. Yeah, let me just say that this model has parameters phi. So p phi y given xt, right? And this is the gradient, which sort of represents how much the pixels need to change for the image to have this classification that you want. That makes sense, right? It's just the gradient of this model, of this probability model, with respect to the image space, like the image pixels themselves. So it essentially is just how much the pixels need to change in the image for this image to be, let's say, a dog. That makes sense, right? So when you're sort of sampling from this kind of a model, you can just shift the pixels that you sort of sample from the model by this amount. And that would automatically sort of push your image towards a direction where it resembles the class more, even though the model did not really have any conditions that it was using, right? the model was completely trying to generate an image unconditionally, but by artificially sort of shifting the pixels towards a certain class using a classifier model, which is completely independently trained, at every iteration, you sort of push that image towards agreeing with that caption a little bit more. So if you keep doing that at each iteration, the model will start sort of generating an image which sort of resembles that class. And the more it adds the features that it make it resemble with the class, the more the diffusion model will try to make it look like a dog. Right? So eventually what will happen is that after 1,000 time steps of this type of sampling, you would get a conditional image without having trained a conditional model. That makes sense? Right? Any questions so far? About anything like just diffusion models, conditional diffusion models, this type of conditioning, and why it would be useful. Anything that's not clear so far? All right, so yeah, so that's score-based model. Now, let's say what you want is that you directly want to condition it on using like a clip model. Okay. So classifier guidance, what is the problem with classifier guidance? The problem with classifier guidance is that you have to train an independent classifier, which sort of already should know the category that you want to sort of generate from your model. So if you train a classifier model, which is an ImageNet classifier, you can only generate images that this classifier can identify. So this classifier can identify, let's say, 1,000 different classes in ImageNet. So you can then only generate images from ImageNet, like with ImageNet, which the ImageNet classes, which sort of already is understood by the classifier model, are the only classes that the model will be able to generate them. But if we want to make this a little bit more powerful and make the conditioning a little bit more robust, we want to directly condition it on text like we discussed, right? So a way to do that by sort of, conditioning it on directly text without having to train a model, which is completely conditional, is you can use the gradient from a clip model also. So if you look at this model, only this part, what does it look like? It's just a probabilistic model which is trying to predict a conditioning signal given the image xt, right? So you can approximate this probability distribution using any kind of model as long as the conditioning signal and the image have some alignment in them, and this model can evaluate that alignment. Like if the model can predict how likely this caption is going with that image, you can sort of use that model to approximate this kind of a probability distribution and then use the gradient with respect to that to sort of then train then sample conditionally from an unconditional model. So in this case, when we want to use a clip model, what we do is that we compute the clip similarity between the image xt and the caption y, and this y, instead of being a class, is now full caption. Because our clip model can take in captions and still, sort of tell you how much that caption is agreeing with this image xt, right? So what you do is that you get the intermediate image xt at the time step when you sort of trying to sample an image from it. You pass it to the clip model, which computes a cosine similarity between your image and the caption, right? And depending on what that cosine similarity is, you backpropagate the gradients, you sort of compute the gradients with respect to that cosine similarity being 1, right? So you're trying to maximize that cosine similarity. So you assume that this cosine similarity should be equal to 1, and you compute the gradients of that cosine similarity with respect to the image itself. And then you can directly use those gradients to shift the distribution that you were sampling from, like we did in the previous case when this was a classifier. Make sense? So now, in addition to being able to condition the model on classes, you can now condition it directly on text, right? Without having to train a conditional model from scratch. And this saves a lot of data because you don't have to, when you're training your diffusion model, you don't have to have a caption with every image that you're training the model with. You can train the diffusion model with just images, which increases the size of the data set that you can use to do that training. And then you have a separate clip model, which is trained with images and text pairs, and then use that clip model to sort of condition this unconditional diffusion model, right? And it still works. It's yeah, it was one of the better models that was working before classifier free guidance came out. Okay, So now let's look at classifier free guidance. Classifier free guidance, the math is slightly more complicated. If you look at the slides, it has like everything, sort of explains it well also. But I want to give you like sort of a intuition for what is happening here. So from the name classifier free guidance, you can already sort of get a sense of what we're trying to do. So we're trying to still conditionally generate images, but we don't really have an extra classifier to guide the model anymore, right? So in that case, what do we do? So during training, what we do is that in addition to training an unconditional diffusion model, you also train a conditional diffusion model with it, right? So you have like conditions or like paired captions or extra conditioning signal data for all the images that you're training your diffusion model on. But a certain number of times, let's say 10% of the times, you just drop the condition. So like 10% of the time you just drop the condition and force the model to just generate the image unconditionally, right? And what this will do is that you will automatically generate, like train two models at the same time. The model which is conditional, which is generating, let's say, an image given a given condition, as well as you also train a model which is generating images unconditionally. So you would sort of have both of these models trained together simultaneously, right? And what is the benefit of doing that? So the benefit is that when you're trying to sample from a model like this, you have, let's say, a condition C given to you, sample with this condition, okay? So you do two things. First, you get a distribution of just P of xt without taking the condition into account, right? So you just get a normal unconditional sample and you get, let's say, this distribution, okay? So this is the distribution that you get when you are only unconditionally sampling the image. Then, because you have also in parallel trained a conditional diffusion model, you can get a conditional distribution as well out of this model by using the condition C, right? So because we are able to get both of these distributions, we get another distribution which is just conditional, right? Okay. So now imagine that you have both of these distributions sort of figured out. And what you want to do is that you want to make the image agree more with the caption, right? And you want to sort of make sure that this conditional part of the sampling is taken into account more than the unconditional part. So what you can do is that you can already see that the peaks that are present in the unconditional distribution are the peaks that are not very useful for your conditional image generation, right? Because these peaks are present irrespective of what the condition is. These modes of collapse, where the data is sort of highly represented in the distribution that you have trained, is already sort of representing all the peaks that you would get if the condition is not present. But given the condition, you get some other peaks as well. So because of having both of these information, what you can do is that you can identify the peaks that are only present in the unconditional distribution and mute those peaks in the unconditional distribution automatically, right? And you can then, the peak that is only present in the conditional distribution, you can sort of push it up and make sure that the model samples an image which is like agreeing with the caption way more than a general distribution would, right? So that is the intuition behind classifier free guidance, where you don't have to have like a classifier at all. You just train like two diffusion models in parallel, a conditional diffusion model and an unconditional diffusion model. And this is also done very easily because you're just training a conditional diffusion model and just dropping the condition randomly 10% of the times or 20% of the times. And that would sort of train both of these randoms together. And then you can sort of use this formula, which is essentially just doing that with some weight parameter, sort of taking two distributions into account and sort of composing them together such that the first one, the unconditional one, is taken less into account as compared to the conditional, right? And then you're able to generate like conditional samples directly from this. All right. Okay. So now let's just look at some examples of the models that are working these days, and see what kind of architectural differences that they represent, and which one works better and how these are working together. So the first model that sort of captured people's imaginations was the Glide model by OpenAI. This model was generating already 64 cross 64 based diffusion images, and the images you can see on the right really agreed very well with the captions that they were passing. In this model sort of at a base resolution generates a 64 cross 64 image. And then there's a conditional up super resolution model. A super resolution model is a model that takes in like a low resolution image, and given the condition, it generates like a high resolution version of the same image. So it's not really adding any content, it's just increasing the resolution of the image. So the base diffusion model that you have to train only works on 64 cross 64, and then you upsample those images to be larger, to 56 cross 56 versions of themselves. And this model is sort of unconditional, but it's conditioned using the clip embedding. So the diffusion model itself is trained unconditionally, but sort of the sampling is done using clip guidance, where, as I said, that you estimate the score PA of x comma y using the cosine similarity, and which is sort of in turn an approximation of this classifier model, which is Py given x, right? And then you get the gradients with respect to that and sort of sample as such. Right, and then after Glide, OpenAI released another model, DALI 2, which was the main one that sort of blew up, and everybody sort of was aware of this field of research as well. Here you can see that the model sort of already generates a very high resolution image. It directly generates a 1K cross 1K conditional image. The base resolution of this model is 256 cross 256, and then they use like sort of an upsampling super resolution model to make it bigger. Even this model has different architecture. Here, instead of using classifier free guidance or clip-based guidance, this model directly conditions on the text captions, right? And it does that as such. So there are two stages in training such a model. The first stage is to train like a clip model, right? Because we want to represent the captions of the image as accurately as possible, right? So when we want to condition the model on text, so when we want to condition the model on this text, we want this representation of that text to be as accurate to the text as possible, right? So to do that, what we do is that we train a clip model, which is just taking the image, encoding the image into a representation, and then applying a clip objective that we have already seen in previous classes to train a multimodal alignment model, which can tell you the similarity between a given text caption and a given image, right? So once you train a model like that, you can now sort of assume that this representation that the model is generating is very informative of what kind of images it goes with. Okay, and then you can use the text encoder that you've trained as such to sort of embed the text you want to condition the diffusion model on. You take the text, you condition it using this clip's text encoder, and then you apply like a prior function which converts this text representation into another representation that the model sort of can handle better. And this prior function is just like any neural networks. There are two versions that they've given. The first one is an autoregressive model, and the other one is another version of a neural network, but it's just a function that sort of transforms the model, transforms the embedding so that the model can learn and sort of fine tune it better based on how it expects the representation to be. And then the decoder is just a unit model, as we discussed, and then that takes the representation of the text and generates the image that sort of agrees with it directly as a diffusion model. All right. Okay, yeah. So the prior, there are two types of priors. The first one is an autoregressive prior, and the other one is a diffusion prior. Both of these sort of have like slightly different architectures, but you can just assume that it's a neural network that sort of transforms the images from the text embedding space to the image embedding space. Right? There are more details about these models, but you can sort of look at that in slides. So the next model that came out was this model Imagen by Google. This model also is very high resolution. It directly generates like 1K cross 1K images directly, and this sort of achieved exceptional photorealism and had like really high qualitative and quantitative results. The architecture of this model is way simpler than any other architecture, which makes it even more powerful because you can very easily understand how it's working and also sort of modify it to based on your own needs. So what it does is very simply, it has a frozen text encoder, which is a language model, which is completely trained separately. So you can just pick a language model off the shelf. Like for example, these days, like even a GPT model or a pre-trained transformer, which is just sort of representing captions or text as a vector. You can pick any language model like that. And then you pass like a certain text, you get the text embedding from the frozen language model. So the language model does not need to be trained also. So you can just pre-train like a language model, just freeze all of its weights and just get a representation of the text as an embedding. And then you have a text to image diffusion model, which directly takes in that embedding, takes into the embedding into account, and then just trains the diffusion model, which is completely conditional, directly taking the embedding into account. And that would generate like a 64 cross 64 image. And then you have like two stages of super resolution where you go from 64 cross 64 to 256 cross 256, and then another super resolution model, which takes it from 256 to 1022. So a very straightforward, simple architecture. It is amazing that how well it works. This also sort of uses classifier free guidance while sampling, because you can see there are no guidance models being used here. So you can directly use classifier free guidance because the model is automatically intrinsically conditional as well as unconditional. And it is made unconditional by, again, dropping these captions randomly 10% of the times during training, right? Okay. This is some results from the paper. All right, so now finally, let's look at one example, like a practical example of how such a model can be useful in like a realistic, problem setting. So here, let me define a problem for you. The problem is that you have these nuclei masks, which sort of tell you which type of nuclei is present in the patch and what location it's present at, right? And what you want to do is that given this mask, you want to generate a synthetic image, which is so realistic that people or like experts or even neural network models are not able to distinguish this image from a corresponding real image, which was already paired with this data, like paired with this mask. So what would be the use of a model like this is that if you have like a certain number of paired image and mask pairs, you can train a model like this, and then the model can just randomly generate any realistic patch which does not exist in the dataset but agrees with the mask that you give it, right? And this can be used to generate like an arbitrary amount of arbitrarily large amount of data to to generate like an arbitrarily large amount of data and use like downstream models to sort of train nuclei segmentation model on it, or even train like pathologists and sort of generate samples of different types of cells which are less represented in your dataset, so that the model can sort of then pathologists can learn from these images more. And you can also sort of generate, like for example, these epithelial cells are more common in the data set as opposed to, let's say, a plasma cell. A plasma cell is very rare in these data sets. So what you can do is that you can generate way more samples of plasma cells, and that can then be used to train downstream models and also pathologists to show them, what these rare types of nuclei cells and what microenvironments look like. Okay, so in this work, what we want to do is that we want to condition on the 7-channel nuclei mask, right? So here the conditioning signal, instead of being text, is just a 7-channel nuclei mask. That makes sense? And we want to condition it on this 7-channel nuclei mask to sort of make the model generate images that are consistent with that mask. So look at this architecture, right? So we'll go, so we'll go over this architecture step by step. So the first step is that you sample some data, right? So you get an image from the data set, which is, let's say, an image X0. and you get a corresponding mask with the image. And this is already present in your data set because you're training on a paired image conditional signal data set. So you already have the mask and the image, right? You then split the mask such that each channel has a different type of nuclei in it, right? So you split this into a 7-channel mask where the first 6 are 6 different types of nuclei, and the seventh channel is just and the seventh channel is just the edges, and that is to make sure that the model understands where each of the nuclei boundaries are, right? So this 7-channel mask is then composed into the 7-channel conditioning signal Y. You then sample a time step and some noise, right? This noise is sampled from a 0-1 normal distribution. It's just random noise. This time step is uniformly sampled between 0 and capital T. And capital T is the number of diffusion steps you're using to sort of train a model like this. Once you sample both of these, you can then use the forward diffusion to noise this image, right? You add T time steps worth of noise into this image and get a noise version of the image, right? That makes sense? You take the time step, you take the original image, and you take the noise, and you use all of these three together in the forward diffusion process to give a noise version of the image. That makes sense? And this noise, in addition to this noise version of the image, you also know what the time step is. You pass both of that to your reverse diffusion denoising model, which is this. That takes into account the conditioning signal as well. So this model takes in the image xt, which, like we had discussed, is just phi theta is trying to generate x, sorry, x t minus 1 given xt, the time step t, and the conditioning signal y, right? So this is a model that does that. This one sort of predicts the amount of noise that was added to the model, as we had discussed that is a practical consideration that works better. So you take in the noise image, the time step, and the conditioning signal. The model predicts the noise that was added to the model. We already know what the noise was that we added to the model. So we just compute a loss between the noise that the model predicts and the noise that we have already, and then you optimize this reverse diffusion model based on that loss, right? That makes sense? So it's just putting together all the conditioning, all the diffusion model and the conditional diffusion model stuff that we have sort of seen so far into solving a practical problem, which is generating synthetic nuclei patches given a conditioning signal, right? So this is how an architecture like this would work. Once you sort of do that, you can see that the model sort of already beats all other kinds of GANs and other types of diffusion models, which are unconditional and different, like a generation before when diffusion models came out. You can already start generating like very hyper-realistic images based on these metrics using diffusion models because they're just more powerful than other generative models that we have so far. And this is what you see when you, and this S is the strength of the classifier free guidance that we are using during sampling. So as you increase that, you can see that if you keep increasing this value, the model will start focusing on this nuclei more and more because increasing the classifier free guidance scale is sort of like increasing the amount of importance the model is giving to the condition signal. So if you keep increasing it, the model will take into account the nuclei mask more and more seriously, and that would sort of increase the like how much uh, attention the model places on these nucleus. Right. All right. So, are there any questions so far, all about diffusion models before we move on to graph neural networks? Any questions? No. All right. Okay. So let me just shut down the slides now because. Okay, so the next topic that we want to cover in this class is graph neural networks. And we were supposed to sort of finish graph neural networks today, but because we sort of delayed with the diffusion models and everything, I'll sort of introduce it today, and then we can continue it in next class most likely. And if not, then we can sort of just consider this introduction as, like how much we learn about graph neural networks. Okay. All right, so first some notation. What are graph neural networks, right? So let's just define what a graph is. So graph is just made up of two things. The first is edges, which represents relationships. And the second thing is nodes or vertices, which sort of represents the elements of your data or the data points directly. Okay, so a graph is just a combination of the edges and vertices. Okay, so these are V and these are. Right, so a graph would be something like this, where you have different nodes, and these are just sort of randomly connected to each other. And the direction and the strength of these connections, these edges, sort of represent the relationships that these elements have with each other, right? And any kind of data which can be represented as a graph can be arranged into this form of nodes and vertices that sort of represent that kind of data. And a very natural data that already intrinsically is in this form is social network data, where these edges can sort of represent like your connections. Like for example, in a network like LinkedIn, each of these nodes can be different people, and these relationships can be the connections that they have. So if let's say you are A, B would be your second degree connection, right? So something like that, like any kind of data that is naturally arranged in a graph can be used here to do some analysis on it. Right? So what does the graph neural network do? So you start with a graph like this. The graph is arranged manually by humans who are trying to solve a problem. So depending on what problem you're trying to solve, you represent your data in form of a graph where you define what these relationships are and how you are sort of interpreting those relationships or the edges in the context of your own problem. Then you sort of get an initial representation of all of these sort of nodes. Like by representation, I mean it's just a vector which sort of represents the information in this node, right? So for example, each of these nodes is represented by a corresponding vector, VA, VD. And initially, all of these vectors can be randomly initialized, or if you have additional information about your data or the structure of the graph, you can initialize them with some informative vector representation that you can come up with. So for example, if this graph is made up of words, you can then initialize all of these words as like the uh, like the word embedding or the word representation using a different model as the initial representation of these nodes. Okay. Once you have a graph like this, what a GNN does is that you feed this graph into a graph neural network model, GNN, and that would give you the graph back actually. So A, B, C, D with the same edges. But what would have happened now is that the representations of each of these nodes would be updated by taking its neighbors into account, right? Yeah.
How do we define those vectors? Like, what is it?
Yeah, that makes good question. So these vectors are just 1D, or 2D, like any tensor representation, which sort of converts your data into numerics, right? So if you're representing, like, let's say this is a LinkedIn graph. So each node is a human person, right? So for example, this is just someone. But now you want to represent the information that that person has into some numbers, right? So you just convert the information of an entity into a vector. And this vector can be completely random. So initially, when you design a graph, you can just randomly initialize all of these vectors. What we're trying to do is that as you sort of do these graph neural network updates, these vectors will become more and more informative of the graph and of their neighbors, right?
Like these vectors, they all have the same features.
They have like the same dimensionality of features, like all of these, let's say, are d-dimensional, but what they encode will be different based on what the node is.
So like after we're passing through the GNN, it's not updating the graph, it's just updating the vectors.
Yeah, so it's just updating each of the nodes of the graphs. So it's not really updating these edges at all, like it's not really changing the direction of the edges, but it's just updating all of the nodes by taking into account what edges it shares with which entities. So for example, this B vector will be updated by taking the C vector into account, and the C vector would be updated by taking B, A, and D into account.
So the thing that trying to be learned is the vectors.
Yes, you only sort of trying to learn the representations of these nodes and make them more and more informative about the overall context of the graph itself. Right? So initially, when these vectors are just randomly arranged and randomly initialized, these vectors do not have any information about the overall graph. But once you do these graph neural network updates, all of these vectors will sort of increasingly become more and more aware of its neighbors and of the overall graph in general by extension. Because each of these nodes will be updated by its neighbors, and that will keep happening again and again. And then eventually you'll get a graph which already sort of encodes that kind of structure into the vector representations themselves.
But we are like assuming we know the graph structure.
Yes, you're assuming that this the node connections or the edges are already known, and this is defined by what the problem is and how you're sort of interpreting what these nodes mean. Right? Okay. So how does this update happen? So let's just look at the message passing, the neural message passing that happens in a graph neural network. Okay, so neural message passing. So for example, let's say it's a simple graph with just 3 nodes. We have E, we have D, and we have another node F. This is the representation one. Okay, and these are the current neighbor states, which is like the vector representation of this time. Now you sort of have to model relationships. We are trying to update the node F, right? So what we do is that we first pass the relationship from E to F through a function, and also pass the relationship between D to F through a function, right? And this is just modeling the relationships individually of all the neighbors of that graph. And let's say you extract some information IEF here and some information IDF here. Okay. Now, to update F, you sort of compose these two together into, let's say, some kind of an information I, and we'll see how we do this when we see like a specific example. And then what you do is that you take that information I, then you pass it to the current representation of f, which is h t minus 1, n is just the dimensionality, and this sort of updates the node to, let's say, h times 50. Okay. Sure. And now this vector has information from the neighbors. This makes sense. So let's look at a little bit, closely at how this is happening, right? So by representing this relationship, what I mean is that the model should compose, like identify how, let's say, f is getting affected by both d and e, right here. So overall, when we're updating our value ht here, this one, the formula can be written as, let's say, q is just an arbitrary nonlinear function, h t minus 1, which is the current state of ht, and you take a union, and this can be any operator. I'm just using union because it's the simplest operator, but any kind of operation like a mean or a sum or any kind of operator that does not take into account the ordering of the edge, like the neighbors, like irrespective of whether e comes first or d comes first, this operator should give you the same value. So as long as this operator is sort of independent of the order of the neighbors, you can use any operator here. So here we're using, like, say, union operator, which takes in like just the neighbors of n. This just means that you're only summing over the neighbors, right? So for each of the nodes, you only take into account the neighbors that are sort of directly connected to the node. And then you pass it to an extra function ft, which takes in the previous time step again. Also, k is the, is only represents the type of the node. Sorry, the type of the edge. So these edges could be of multiple types. You can have like bidirectional edges also. Like there are some edges that go like in the opposite direction. So depending on what the edge is, this k only represents the type of the edge. You can pass the previous time step, the k, and the h t minus 1 j. And this is just the representation of the neighbor. So for each neighbor, you do this computation, you union them together, and then that sort of using a new function q, you compose that with the previous time step of the node that you want to update, and that sort of updates the node for the next time step. Make sense? Right? So what do you do with this though? Like there are no tasks, it's just updating it randomly by taking into account the neighbors. So like what is the use of doing all this? The use is that there are 3 different types of problems that you can solve using graphs like this. The first is node selection. Which means that once you sort of update these graphs based on the representations of the neighbors, what you can then do is that you can select one node out of this based on a task that you define. Like for example, you have like a LinkedIn graph and you want to select the most influential person out of the graph, right? So what you do is that you keep updating the nodes again and again using a graph neural network algorithm, and eventually, sort of once all of the nodes are updated, you check which node has like the highest values based on a certain metric that you design, and then that would give you what node to select, right? So that's node selection. There is node classification, which is, as it sounds, you have like different nodes and you have to sort of classify each of the node into different types. You get the representation updated by the graph algorithm, and for each sort of node, then you can pass this representation into a separate neural network or a multi-layer perceptron to make the classification for each node. In addition to that, you can also do graph classification, which is sort of just classify the whole graph into like different categories. And that can be done by sort of updating the representations of each of the nodes several times. And then once all of the nodes are sort of updated properly, you can compose all of the nodes together to get a representation of the graph and then use that into a separate neural network algorithm to sort of make the classification. And you can sort of even train using the gradient of that multi-layer perceptron to make the embeddings even more informative of that classification problem, right? So these are the three basic problems that you can solve using graph-based algorithms. There are different types of graph neural networks, and I mean, it might take some time to sort of go over one of each of those, and we don't have like enough time left. So what we do is that we just stop here, and then in next class, we can see different types of graph algorithms, and then see how each of those are used for different types of problems. Yeah, you can have like 7 minutes extra as a Thanksgiving. Okay, what this class. All right. See you next time.